Annenberg Media.
Throughout the vast reaches of our solar system, from the tiniest bits of dust and ice to the huge gaseous planets, conditions that might support life as we know it are conspicuously absent. On Venus, for example, a dense, noxious atmosphere combines with a thick cloud cover to trap solar energy with extraordinary efficiency. The result is a surface temperature of about 475 degrees centigrade. On Mars, conditions are not quite so brutal, but hardly conducive to life. The mean surface temperature on the red planet is minus 23 degrees centigrade, and the Martian atmosphere is very thin, composed primarily of carbon dioxide with some nitrogen and argon. But there is one planet in the solar system whose physical properties foster the growth of living things. A planet whose distance from the sun permits moderate temperatures, whose size enables it to hold an atmosphere in which organisms can respire, shielded from cosmic radiation. This is planet Earth, home to an incredibly diverse flora and fauna.
With its abundant water, moderate temperature, and oxygen-rich atmosphere, Earth is the ideal habitat for life, the only such place in our solar system. To understand why the Earth is so extraordinary, it's necessary to trace the historical development of our planet and to understand the processes of nature which operate today. This is what the science of geology is all about. Geologists do more than collect rocks and catalog fossils. Geology is the study of the whole Earth, and the goal of geologic research is to understand as best we can how the entire Earth works.
This planet's geologic activity is driven by what geologists refer to as Earth's two heat engines, one internal, the other external. These are dynamic processes that convert heat energy into mechanical energy, which in turn causes geologic change. The Earth's internal heat engine is powered by heat from radioactive decay deep within our planet. It drives a process known as convection, which causes hot material to flow from the interior of the Earth slowly toward the cooler surface. Earthquakes and volcanoes are results of convection. The Earth's external heat engine is essentially solar-powered. It sets in motion a cycle known as the hydrologic or water cycle that has important ramifications for the landscape of this planet. When rain or snow falls on the land surface, more than half the water returns to the atmosphere by evaporation or by transpiration from plants. The remainder percolates down into the earth to become groundwater, or flows over the land surface as runoff in streams and rivers. Over long periods of time, this moisture at the Earth's surface helps rocks decompose, forming soil. Water washing down hillsides and flowing in streams loosens and carries away the rock and soil particles. The Earth's two heat engines do not work in isolation. Instead, they perform a kind of ongoing balancing act. Mountains originally raised by the Earth's internal forces are worn away by weathering and erosion driven by the external heat engine. These heat engines, working together, provide the fuel for this enormously complex machine we call Earth. And it is the detailed workings of this dynamic planet that geologists are continually trying to better understand.
There's never been a more exciting time to study geology than right now. Since the 1960s, Earth science has undergone something of a renaissance, as new evidence about the way the Earth works has replaced old, simplistic perceptions. This new knowledge has been blended into a single, inclusive theory of Earth history and function, the theory of plate tectonics. We now know that the outer skin of the Earth is composed of individual pieces, or plates, that slide around on a partially molten layer below. Geologists are struggling to understand the processes which move the plates and the interactions between the plates themselves. But today, there is perhaps an even more compelling reason for unraveling the mysteries of the Earth's interior: the need to locate the natural resources upon which civilization depends. Minerals, petroleum, fresh water, fertile soil. These natural resources are not in unlimited supply, and we are consuming them faster than they are formed. Geologists play a crucial role in this challenge. Using their knowledge of the way the Earth works, they uncover new sources of minerals and fuels and plan ways to extract them, economically and with minimal harm to the environment.
Geologic resources are essential for modern civilization. With the exception of solar energy, nearly everything humans depend on comes from the Earth.
Everything that we built our civilization with, our homes, the car that you drove in with today, what was it made of, how it was fueled, the chair you're sitting on or your desk, the pencil you write with, all the materials that we live with on an everyday basis come from the Earth. Somehow they've got to be extracted from the Earth, and the geologist has that principal role.
While there is a wide range of resources which play key roles in modern civilization, it is petroleum that garners most of the world's attention. For geophysicist Stephen Scott, the search for oil and gas is an ongoing challenge. Oil companies typically use seismic studies of Earth's crust to assist in locating reserves. One technique, known as reflection seismology, is especially useful.
In reflection seismology, what we try to do is generate that source or that shock wave ourselves and try to reflect that off of subsurface rocks and record it at the surface with geophones. We do that by sending out a truck into the field, which we have a truck called a vibroseis truck that actually shakes the ground. A vibroseis truck would shake the ground in an up and down fashion, much like a jackhammer on a construction site shakes the ground. And so what we're trying to do is use a technology so we can see the secrets of the Earth below.
Because the shock waves interact differently with different kinds of rock, reflection seismology helps geophysicists find geologic structures that commonly contain oil and gas. Such structures can be detected not only by seismic techniques, but by observation from aircraft or satellite as well. This method of long-distance viewing is called remote sensing.
It's a way of looking at very large areas very quickly and getting an overview. Particularly since the advent of satellite remote sensing, we have had the luxury of being able to look at very large areas of the Earth's surface at one time and get an integrated idea of what's going on. What remote sensing has done, or satellite remote sensing particularly, has given us a chance to look at the interrelationship between widely separated features and see those in a way that we've not been able to see before.
In one recent investigation of the potential oil and gas reserves of Pakistan, 28 separate images were combined to form a mosaic which showed numerous spectacular geologic structures. Because of their remoteness, many had not been seen by ground-based geologists. This opened up new areas for oil and gas exploration. But remote sensing is by no means limited to the search for new sources of energy. It has also been used to study changing vegetation patterns, locate mineral deposits, track pollutants, and search for another critical resource, groundwater. The amount of water lying underground is vast, more than 30 times the total supply of water stored in all the world's lakes and rivers. Civilization depends heavily on groundwater, and as population rises, this resource becomes increasingly valuable.
The thing is that groundwater is almost always there, but it may be too deep to be economical to drill. It also may not be of good purity. Today we have severe problems with pollution, contamination, and groundwater, as we go deeper, gets older, gets hotter, and gets saltier. So you don't want to go real deep.
In the Southern California area, there are a number of factors that create a favorable environment for groundwater, including very permeable soils, a large storage capacity, and a steady supply of surface water. At the Orange County Water District, Jim Goodrich is responsible for managing the groundwater supply. He is concerned both with the quantity and the quality of available water.
So what we've done at Orange County is developed a very sophisticated groundwater monitoring program which uses surface water sampling, production well sampling, and dedicated monitoring well sampling. Our monitoring wells are drilled to a depth of about 1,500 feet and isolate and tap up to 18 zones that we can monitor individually, so that if a contaminant is coming towards us, towards a production well, we can find it before it becomes a problem and institute a mitigation.
Like water, soil is a geological resource essential to sustaining civilization. For farmers like Wayne Sopland, who lives in California's Mojave Desert, maintaining a fertile, plentiful supply of soil is an ongoing struggle. The chief threat is erosion, which can be caused by either rain or wind.
The rain is a fairly minor situation here in the desert. We only have 4 inches of annual rainfall. Sometimes it all comes at one time, and we do have some runoff from sloping parcels or some stream bank erosion in streams that are normally dry. But that's relatively minimal. Our major problem with soil erosion results from the wind. And that can happen at any time of the year, winter, summer, fall, doesn't matter. And we have fairly heavy winds for long periods of time, and we have to take a number of precautions related to that.
To dissipate the strong winds that can remove a half-inch or more of soil in a single day, Sopland has planted dense rows of trees known as windbreaks around his fields. He's also turned to the United States Department of Agriculture for additional ideas. After visiting Sopland's farm and learning about his primary concerns, soil conservationist Rick Aguayo drew up a soil management plan.
Manage irrigation waters a little more efficiently.
This plan included suggestions about how frequently to plow the fields, as well as recommendations concerning water management and crop rotation. Along with the use of windbreaks, these soil conservation techniques are making a significant difference on Wayne Sopland's farm. These improvements are not just quick fixes, but substantial changes that will keep Sopland's soil productive for years to come. Whether the specific issue is soil, minerals, oil and gas, or water, there is a growing awareness that modern civilization is rapidly depleting Earth's supply of precious natural resources. And it is geologists who are devising new ways to more intelligently extract and conserve these resources. But their role extends well beyond the hunt for resources. Earth scientists are also deeply involved in helping the world's population safely coexist with this planet's many geologic hazards. One of the more serious hazards in terms of potential destruction is volcanic eruptions. And while there is no way to eliminate eruptions, scientists are continually refining their techniques for forecasting such events.
Probably all volcanic eruptions are preceded by and accompanied by measurable changes in the physical or chemical state of the volcano. And one of the principal means of monitoring or measuring the changes, at least in the physical configuration of the volcano, is by means of what we call ground deformation studies. And this simply is just a term for measuring the changes in the shape of the volcano.
In a research project underway in Alaska, geologists are studying one of the most powerful volcanic events of the 20th century, the 1912 eruption of Mount Katmai. Scientists there believe this is an excellent setting in which to learn more about how explosive eruptions occur.
It all happened in about 60 hours. We know exactly when, the date, the time. And also, which is also very unusual, is that it came up through an area where nothing much had happened volcanically before. It came up through a very simple part of the Earth's crust. And finally, the system is perfectly preserved. Usually in events in this type, there's an enormous amount of collapse at the vent, the area is flooded by water, or it occurs in a very complex area and it gets eroded away. In this case, the whole system is perfectly preserved. So the size, the simplicity geologically, and the preservation make it an exceptionally good place to try to understand the basic processes of explosive eruption.
Although much data have already been collected, the Katmai project is still in its preliminary stages. Research may continue here for years, bringing with it new discoveries that will improve our understanding of volcanoes. Volcanic activity potentially threatens millions of people worldwide. But equally threatening is another common geologic phenomenon: earthquakes. Geologists have a general understanding of how earthquakes occur, and the areas most prone to earthquakes have also been identified. But much remains to be learned about these events. While scientists have successfully identified some signs of impending earthquakes, these precursors give little clue as to exactly when an earthquake will strike or how large it will be. Along one pastoral stretch of the San Andreas Fault near Parkfield, California, scientists hope to learn more about earthquake precursors and what actually happens during an earthquake itself. Geophysicists are using a sophisticated array of devices to closely monitor movement along the fault. The objective is to spot any changes that might signal an impending quake.
The Parkfield experiment has three goals. One goal is to try to issue a short-term prediction of the Parkfield earthquake, and that would, if successful, be the first time we've ever done something like that in this country. The second goal is to record the details of the earthquake generation process in as much detail as possible. And the third goal is to take advantage of the fact that we'll have a moderate earthquake to record some of the effects of the earthquake, such as the amount of shaking that occur at different distances from the fault.
While earthquake prediction is a significant goal for geologists, most stress that earthquake preparation is even more important.
First of all, we must try to shore up existing structures and make them more earthquake resistant. There is no such thing as an earthquake-proof structure, not at least an economically built one. but we can make things earthquake resistant so that loss of life is minimal, maybe zero loss of life. That can be done now and should be. It's very expensive, but we must re-strengthen old buildings, old structures. Furthermore, we have laws on the books that prevent building new structures in earthquake-prone areas where the dangers are excessive. Those laws should be maintained and perhaps even strengthened. We have also building codes that require modern buildings to be built sufficient to withstand intense ground shaking. Continued research into building structures of all sorts and their resistivity to earthquakes must go forward. That's something we can do now. We don't need to know when the next earthquake is coming to know it's important to build buildings that stay up and don't lose windows and facing material in the event of an earthquake.
Even more destructive than volcanoes and earthquakes are mud flows, landslides, and other related earth movements. Every year, they exact a staggering toll on populated areas. In some places, people have attempted to live with land movements, although not always very successfully. When new construction is planned for areas with slopes, geologists are often called upon to evaluate potential landslide risk.
Let's take a look, see where we are. You got your compass? Yeah. It's got the limits of the slide here.
First, the proposed building site is mapped.
These cuts down.
Next, drilling is done to give the geologists a direct view of the subsurface structure at the site. Along with soil samples obtained during the drilling process, this provides much needed data about the history of landslide activity in the area.
As we drill the hole in that area, we will be sampling the material to determine how strong it is. We will also be describing it in terms of its soil characteristics such as grain size, moisture, color, a variety of types of characteristics which will be useful to the engineers in the office when they determine whether or not the material will be suitable to stand in a slope or to be reused as fill somewhere else on the site. Once we've worked with our engineers in the office and determined whether or not the slopes that are proposed will be stable, what type of removals are necessary, we'll prepare a report with all this information that we can then share with the client.
After evaluating the stability of a site, geologists can make recommendations about whether a building project should be undertaken. Ultimately, this can help minimize the risk of death and destruction due to landslide activity.
The human population of this planet is now close to 6 billion, and it's increasing exponentially. Many of the world's population centers are located in areas threatened by natural geologic hazards, such as earthquakes, volcanic eruptions, and landslides. Geologists are working to understand the exact nature of hazardous geologic processes like these, and then applying this knowledge to reduce the toll on human life. The teeming industrialized societies that have resulted from this population explosion have also spawned environmental problems, which are only now being recognized. Geologists are actively involved in the battle to overcome a broad range of these problems. And as the world's population continues to grow, the environmental challenge looms ever larger, and the stakes grow even higher.
Today's Earth scientist is expected to play a dual role, helping to locate valuable natural resources, while at the same time protecting the environment, which provides those resources in the first place.
Geologists and earth scientists in general are the scientists who are capable of dealing with the problems of resource extraction and environmental protection. We therefore have a dual obligation to society to maintain our material base by providing the resources to the populace and by maintaining some control over environmental degradation. We can't have it both ways. Every time we modify the environment to some extent, it is degraded. We can't make it better, no matter what some of the ads may say. So we've got to be certain that we use our resources as wisely as possible. Earth scientists know the nature of the resources, where they're located, what their occurrence is, how we can extract them efficiently. That must be an important goal for the future, to make certain that we use our resources as efficiently and effectively as possible, with as little waste as possible, for future generations.
Whether the resource in question is fossil fuel, soil, or groundwater, geologists are charged with a unique responsibility: providing the public with a fundamental awareness of how planet Earth functions.
Perhaps more than any other science, geology has influenced the evolution of civilization and the history of nations. Natural geologic hazards have devastated cities and contributed to the fall of governments. The geographic distribution of fossil fuels, precious metals and gems, and industrial minerals have created empires and caused wars. It has allowed the citizens of some nations to enjoy boundless prosperity, while those living in less fortunate regions struggle to eke out a marginal existence. But geology has given us more than oil and metals and predictions of natural disasters. The science of geology was founded not for economic benefit, but from human curiosity about the Earth. And it's provided us with a way to understand this planet we call home. Geologists rarely conduct experiments. It's not possible to carefully control the geologic conditions in this global laboratory. Instead, working from the shreds of evidence that have escaped erosion and destruction by geologic processes, geologists have pieced together the details of Earth function and history. The image of Earth from space is a kind of visual metaphor for the science of geology. From space, we can perceive only the dimmest of clues about the planet lying beneath the swirling clouds and deep blue oceans. To unlock the mysteries of our complex and beautiful planet, and to understand its significance to our own lives, we must carefully examine the processes and products of geologic activity. And during the course of Earth Revealed, that's exactly what we propose to do.
Annenberg Media. For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.